All right, you guys, this is our last section of the class. That is so exciting. Well, I'm not super excited because I'm just sad for you that you're not going to have math for a while. But I just wanted to do, well, I say a quick lecture, but I think you know me by now that it's probably not going to be super quick, which, is okay because what I want to do is give you what you need to understand. So, all right, so let's see. So what I wanted to talk about was just this. I know I want you to read through the book. I don't want to, say that to you or reiterate what you've already read. I guess I do want to reiterate it, but I'm not going to go over it in detail again. But I wanted to talk about this idea of a Poisson random variable. I do not speak French. I had to look that up on how to pronounce that. Poisson, I think is how you say it. My other students were telling me it means fish in French. So it's not a fish variable, but we say that X is a Poisson, I'm going to butcher that, random variable. So I'm sorry for those of you that know French. Okay, it's a Poisson random variable is a variable, okay? X is a Poisson random variable if, okay, and the idea here again, so remember at the beginning of the section, we're talking about discrete probabilities again, or discrete outcomes, excuse me, not probabilities, but my discrete outcomes. So the only real difference between this section and what we've done before is that really these outcomes could hypothetically go to infinity, okay? So when we define, your expected value and your variance, you saw that they define that and they use, this little plus dot, dot, dot. Oh my goodness, excuse me, I'm so sorry. Plus dot, 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 and we found, if you do P1 plus P2, if these are my probabilities, we have this dot, dot, dot because we don't know how many possible outcomes we have. It could possibly be infinite. But if these P's are the probabilities that outcome is going to occur, of course, they have to sum up to be 1. And you saw that with the variance is the same definition, except again, there's a dot, 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 okay? So when you look at this, some examples, one example we're going to look at is like if I took a newspaper page and I counted the number of typographical errors on there, that would be an example of this type of random variable, and it's a discrete outcome, right? There is not continuous. I couldn't have 4.125 errors. I either have 4 errors or 5 errors. That's what we mean by discrete, okay? So X is a Poisson random variable. Let me see how I want to state this. If the associated probability, okay, for an outcome, let's just say that outcome, it could be like 2 errors or 4 errors, or let's just say n errors. So the associated probability for an outcome n is given by, okay, and we found that the probability then P sub n equals this lambda, which is this parameter, okay, that they kind of talked about. That will be given to you, or you'll be able to find it all over. Now that isn't n. I love that joke, sorry. That's n factorial times e to the negative lambda. And recall n factorial, right? N factorial, you just take n times n minus 1 times n minus 2 times dot, dot, dot times 2 times 1, right? So for example, like 5 factorial would be 5 times 4 times 3 times 2 times 1. Used a lot in probability theory and stuff. Okay, so the Poisson random variable is a Poisson random variable if the associated probability for an outcome, let's say n, is given by this probability function right here. And we have where e of x, my expected value, this is pretty nice, is actually just equal to that lambda. And they proved that, I think they proved that for you in the book. And the variance is equal to lambda also. So this stuff's pretty nice. It plays nicely with others, gets along well with others, okay? So I just get that lambda for my expected value and my variance. All right, so let's do an example. And before we actually go to the example. There's some stuff in this. We didn't do chapter 11, so I don't do infinite series in this class because, you know, that's an important topic for a regular Calc 2 class. Not that you guys aren't regular, but not maybe a business-focused Calc 2 class. And so you can read a little bit about how when we add up an infinite number of things, it can actually equal 1, and that's kind of an interesting topic. If you'd like to know more about that, you are feel free to email me, and I'd be happy to explain it to you on to why, right, all of these guys should add up to be 1, because we know our probabilities should be 1. So I just want to point that out, and I apologize if you feel kind of cheated on that. But I would be happy to explain it to you if you would like me to. Okay, so let's look at an example. All right, so we have the number. This is the example I was talking about of typographical errors per page, okay, on a newspaper. Has a Poisson distribution. Okay, and there's an average of 1.5 errors per page. Okay, so this is kind of setting us up. So again, let's think about what this random variable does. What is the experiment that's going on, right? I grab a page at random and I count the number of errors on the page. That is my outcome, okay? That's what this is doing. And what we're saying is if I take all of those outcomes and I look at its distribution, it has a Poisson distribution, okay? All right, so my first question then is, what is the probability? I'm getting a little lazy here, not actually write that all out, that a randomly selected page of the newspaper, so we'll just say a randomly selected page will be error-free. All right. Okay, so what we need to go back to is we know the probability for the outcome n is lambda to the n all over n factorial e to the negative lambda. Okay, did I write that right on the last page? Hold on. Yeah, okay, good. I thought for a minute that maybe I hadn't written that correctly. Okay, so what is the probability that, okay, the probability that we have 0 errors. So the probability that my outcome is 0, that's the question. So what we want to know p sub 0. That's what I want to know. What's the probability I grab a paper and I have 0 errors? So what I need to find, I know n is going to be 0, but more importantly, I need to find lambda. Well, we've been given lambda really just by this guy right here. Remember, we know that the expected value of a Poisson distributed random variable is equal to its that value, right? That lambda value. What am I looking? The word I'm looking for, parameter. The parameter lambda. So I know in this case, in this problem at all, I know I'm going to have 1.5 to the n over n factorial e to that negative 1.5, okay? And so what is p sub 0? This is going to be 1.5 to the 0 all over 0 factorial e to the negative 1.5. All right, so a couple things here that you need to know about factorials, and I think they mentioned this in the book. I'm just rooting around for my calculator. 0 factorial, I know this is weird, but this guy right here equals 1, okay? So 0 factorial is 1, 1.5 to the 0 is 1, so I basically get e to the negative 1.5, which if I just put in my calculator, I get not 0.15, 1.5, I get 0.223. So I have about a 22.3% chance that a randomly selected page will be error-free. No errors. Okay. All right, let's do part B. what is the probability a page selected at random, so I'm just going to put a page, has 1, 2, or 3 errors? So a page selected at random, what is the probability it has 1, 2, or 3 errors? So basically I want to take the probability I have 1 error plus the probability there are 2 errors plus the probability that there are 3 errors, okay? So this is going to be then, again, 1.5 to the 1 over 1 factorial e to the negative 1.5 plus 1.5 squared over 2 factorial e to the negative 1.5 plus 1.5 cubed all over 3 factorial e to the negative 1.5, okay? So this is going to give us I want to take the probability I have 1, probability I have 2, the probability I have 3, and when we have an OR probability, what we do with that is we add them all up, okay? I want to show you really quick on the calculator. Whoa, look at that calculator just come in. How I would do this. So if I go back to here, notice what all of these have in common is this e to the negative 1.5, okay? So what I'm going to do, don't want a new email. I'm actually going to put this all in my calculator at once, and I'm going to show you how to do that. So I'm going to put a parenthesis. I'm going to do 1.5. Okay, so that's going to be the first one raised to the first power. I don't need to do anything with that. Also, if I look at this, it's divided by 1 factorial, and 1 factorial is just 1. Then plus 1.5 squared. And then I want to show you something here. I'm going to divide this guy by, and the great thing is you can get, 2 factorial you could figure out. That is 2 times 1. But if we get larger numbers, if you go to, so let's put the 2 in. If you go to math in your calculator and come all the way over to probability, there is the factorial right there in number 4. So I'm going to just click number 4, and that gives me the 2 factorial plus 1.5, right, raised to the 3rd power. Come down off of that exponent. Oh, I see it. I have too many. There we go. They would have gotten mad at me there. Come all the way over, divided by, and again, 3 factorial isn't that big of a deal to do. It's 3 times 2 times 1. But if we get larger numbers, let's go to math. I'm actually going to scroll over the other way to probability, pick number 4, and that gives me my factorial. Close my parenthesis. So what I've done there is I've taken this plus this plus this. Then I close my parenthesis, I grouped all that, and that whole thing is going to be multiplied by, I don't need the times sign, but this e to the x to the negative 1.5, okay? So just want to show you kind of a way to do that on a calculator that's a little easier than having to do each single one, but each one is being multiplied by the e to the negative 1.5, so we might as well take advantage of that. Press enter, oh, and of course I have an error. So let's bring that up again. And let's see what I did wrong, people. E to the 1.5 I think is okay. 1.5 to the 3rd is okay. Huh. I don't know why it's mad at me. Divided by 2 factorial. I might need, I wonder if I need that 2 factorial in parentheses. I bet I do. Sorry about that. What I think it might be doing, let me tell you what I think it might be doing. I think what it might be doing is it might be taking 1.5, squaring it, dividing it by 2, and then applying the factorial afterward instead of applying the, and that's just order of operations. That's an order of operations issue. So let me put in some parentheses. You know, as embarrassing as it is to make a mistake on my video here, I'm kind of okay with it because I want you to understand that I do that sometimes. Don't tell my husband, but sometimes I make mistakes, and let's put an inner because it doesn't know. Oh my goodness. Let me see what my go. Oh, Oh, all along. It was just too many decimals. You guys probably saw that. But I would maybe put that factorial in parentheses now that I think about it. I just had too many decimals. That was silly. Okay. So after all that, if you're still with me, I hope, we get 0.71123, let's say. So 0.71123. So we have a 71.12% chance that I grab a page and I have 1, 2, or 3 errors on that page. Okay, I want to do one more example really quick. If I can pull this up here. Let me just clear this out really fast. Okay, so, well, not one, I want to do one more part of this. So find what is the probability that there will be more than 4 errors? Okay, so more than 4 errors. All right, so the probability that I have more than 4 errors, this is gonna take a little bit of work because remember, I can't be like, well, I'm gonna add up 4, 5, 6, 7, 8, 9, 10. When do I stop? We don't know. We don't know the maximum number of errors that we can possibly have on that one page, right? So what I wanna do is I wanna remember that P0 plus P1 plus P2 plus P3 plus P4 plus P5, and then I thank the math gods every day that I have a dot, 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 because this whole thing, my friends, equals 1. Okay, so if this whole thing equals 1, really what I want to know is I want to know the probability of I want all these guys added up. More than 4 errors, right? So how can I do that? Well, I can actually kind of solve for this. I know that this whole thing right here, more than 4 errors, will be equal to 1 minus less than 4 errors, right? That's how we're going to do it. If I want more than 4 errors, I take 1 minus the probability that I have less than 4 errors, and that's going to give me what I want. And so here, you know, there's a reason I already did 0 and 1, 2, or 3. So I know then that the probability, it's meant to be writing it like this, that my random variable is greater than or equal to 4, right? That my outcomes are greater than or equal to 4. It's going to be 1 minus. So remember, P sub 0, probability of no errors was 2, 2, I think 3, 1. Oh my goodness, come on. 2, 2, 3. And then 7, 1, 1, 2, 3. 2, 2, 3. And 7, 1, 1, 2, 3. So if I take that, I would do 1 minus 0.223 plus, making sure I have parentheses. Okay. And I put a 9 instead of parentheses. And what do we get the probability? The probability that I have more than 4 errors is 0.06577. So look at what we have. We have about a 6.6% chance that if I grab a page at random, I will have more than 4 errors, or 4 or more errors. Okay, I hope that makes sense. All right, guys, let's just talk about the geometric random variable, and then I'm going to let you go. And again, I'm not going to go through the whole setup of the geometric variable for you, but I do want to kind of talk about this. So definition, just going to kind of state what they've already kind of set this up for us. So so let's let X be what we call a geometric. If you're still with me, that's awesome. If you had to take a break and you need to come back, I get that too. Okay. Then there exists a parameter P. So instead of lambda, we're going to use P such that these are the probabilities. Again, here, the outcomes again are discrete. Okay, and usually when you're doing this, the outcomes are usually only two possible outcomes. So like an example of a geometric random variable is flipping a coin. There are two possible outcomes. There's heads and a tails. We're going to do an example of rolling a die. I'm not sure how to say that exactly. And that again is just going to be a discrete random variable. There are a discrete number of possible outcomes, such that the probability of n occurring, and we're going to look at these, this is going to be a little tricky. It's p to the n 1 minus p. And I want you to remember here that x, right, equals the number of successes, you saw this in the book, before the first failure. And try and not let your mind get into this idea of what success means and what failure means. It's basically you want to think about of this occurring or of it not occurring. So, you know, when we think about this, if I want to know, you know, what's the probability, let's say I toss a coin and a tail is a success and a heads is a failure. It's not that that's a failure. It's just that those are my two different outcomes. Okay. So if I wanted to know maybe what's the probability that, that I toss a coin 5 times and the 6th time, right, it'd be get a head. So I get 5 tails and then a head. Well, then my n would be 5. It would be the number of tails before I get that head. Okay, so that's the number of successes before the first failure. And you can look, they state this too. I think they prove this for you, but the problem with proving this is you need some stuff about geometric series, which we didn't do because we skipped chapter 11. And you can, again, if you would like me to verify any of these for you, I would be happy to do so. I like doing that stuff. All right, guys, let's keep this lecture under, I want to keep this lecture under 30 minutes. So I have 8 minutes to do that. We're just going to do one example. I think we can get that done. Okay, it's getting mad at me already. That's all right. Okay, so, whoa. Sometimes I don't always know what my surface is doing. Okay, a pair of dice. Die? I'm not sure about the plural of that. Dice, I think, is rolled until a 7 until a 7 or 11 appears. Okay, so this is what we are going, this is going to be a geometric random variable. Okay, appears, and the number, let's just kind of state this. The number of rolls preceding the final roll is observed. Remember, the final roll is going to occur if we get a 7 or 11. And what we mean by 7 or an 11 is if you add up the 2 die, right, we get a 7 or 11. Preceding the final roll is observed. All right, the probability of rolling. Whoa, my G there, a 7 or 11, right? Either one is 2 9s. And let me explain to you really quick why that's true. So when we roll a pair of die, if you had any probability, you probably know this, but if I roll a pair of die, the first dice, right, first dice, there are 6 possible outcomes for this first die, because it's 1 through 6. There are 6 possible outcomes for the second die. So how many total possibilities are there? There are 36 possible outcomes, right, when I roll 2 die. Now, if I look at 7, how many ways can I get 7? Well, I could get 1 plus 6, 2 plus 5, right, 3 plus 4, or 4 plus 3, 5 plus 2, or 6 plus 1, right? Depending on, this is the first die, this is the second die. So there are 1, 2, 3, 4, 5, 6 ways that I can get a 7 by rolling 2 die. And then 11, there are only 2 ways. I could get 5 plus 6, oh, this is getting a little tight, and 6 plus 5. So what are the ways that I can get a 7 or an 11? Well, 7 is 1, 2, 3, 4, 5, 6. 11 is 8. So basically there are 8 out of 36 ways, okay, that I can roll a 7 or an 11. So that's where that 2/9 comes from, just in case you were wondering. I'm sure you were. All right, so A. Determine a formula for P sub n. All right, so P sub n. Here's what we have to think about when you look at this. P sub n, if you go back, and I guess we didn't really state what this was, but this P is basically the probability of a success, right? That's the number of successes before the first failure. And I know this is going to be weird, but for us, in this case, what is a failure? That is going to be 2/9, okay? So what is a success? Well, if you think about this, any of these other ones is going to be a success. So the success would be anything that is not a 7 or an 11. So anything that's not a 7 or 11 are any of the other possible combinations, right? So if I take, that'd be 28. If I take 36 minus 8, there are 28 other possibilities, other sums that I could get that are not a 7 or an 11. And if we simplify that down, that's 7/9. And it would make sense that I either get a 7 or an 11 or I don't. So this is probability I get a 7 or an 11. This is the probability I don't. Those two should add up to be 1 because we got to get something. So a success would be 7/9, right? That's what we consider a success. I know it doesn't, don't think about success and failure as in terms of what they actually mean. Think of them as just two different outcomes, okay? So if I want to determine P sub n, so remember my P sub n is going to be P to the n times 1 minus P, okay? And so P to the n, that's going to be 7/9 to the n times 1 minus 7/9. And so what do we get here? We get 2/9 times 7/9 to the n. I just like to put the term without the exponent first, okay? And what I think of about this is, this is just a probability that I don't get a 7 or 11 each time. And then what's the last roll that I do get a 7 or 11? That probability is 2/9. So I think if you think of it that way, that can be pretty easy. So determine, okay, the probability that at least, oh, I'm not going to make it past, I'm not going to make it within a half hour, yeah. Well, maybe I will. You never know. Let's get rid of some of this really quick so we have some room. I'm just going to, this is going to be our only example, and then I'm going to let you look at the examples in the book. But determine the probability that at least 3 consecutive rolls precede the final roll. Remember what the final roll is if I get a 7 or 11. Okay, so again, if I want the probability that at least 3, that means I want my random variable, I want there to be more than 3 rolls, we're going to have to figure this out again with kind of what we did before. I could have, hypothetically, I could have as many rolls as possible before I get a 7 or 11. That's not very probable, but theoretically that could happen. So what are we going to do? We're going to take 1 minus the probability of 0 plus the probability of 1 plus the probability of 2. Okay, so I'm basically calculating P3 plus P4 plus P5 plus P6 plus ... That all equals 1 if I add on the 0, 1, and 2. So I just subtract. So let's look at what's going to happen here. So the 0. Let's look at what happens up here. I would get 7/9 to the 0, right? I'm going to look right here. 7/9 to the 0 is 1, so I get 1 times 2/9, which is 2/9. Now let's think about that. Why does that make sense? What that's saying is that there are 0 rolls before I get a 7 or an 11. So what that says is on my very first roll, what's the probability I get a 7 or 11? 2/9. Yeah? Makes sense, right? For this next one, okay, if n is 1, I'm actually going to put the 7/9 first. And 7/9 to the 1 is just 1 times 2/9. Again, what I want you to think about that is, this represents the first roll. What's the probability I don't get a 7 or 11 on the first roll? 7/9. What's the probability I do get a 7 or 11 on the second roll? 2/9, right? 1 success, and then I hit my failure. What about P2? So I get 7/9 again, squared times 2/9. Again, this formula, I mean, I think math is magical in its own right, but what this formula really is just saying is, well, look at this guy right here. What's the probability I get 2 rolls and then I get a 7 or 2/9? Well, what's the probability I don't get a 7 or 11 on the first roll? 7/9. What's the probability I don't get a 7 or 11 on the second roll? 7/9. Finally, whoops, my battery's running low. What's the probability that I do get a 7 or 11 on the next roll? 2/9. That's where this formula comes from. If you've had any probability, any kind of statistics stuff, you're going to see this will look familiar to you, okay? So I think we get, I don't trust my notes. I'm just putting this into my calculator really quick. Thank goodness for graphing calculators, huh? And we get 0.471. All right, so I have about a 47% chance that there will be at least 3 rolls before I get a 7 or 11. Kind of cool, huh? I kind of like these. I think they're kind of fun to do. Oh man, I'm over by about a minute and a half, but this is your last lecture for the class. So, you know, I hope you enjoyed it. I have enjoyed it. I've really enjoyed doing these lectures, even though I'm just talking to myself in my office and it's kind of strange. But if you have any questions or if I made any mistakes, which I can guarantee I probably did, will you please send me an email and let me know? And as always, let me know if you need any help.